testing, test, testing, that works. So why? Testing, okay, let me call in again. Testing, can you hear me now? Okay, good, thanks for letting me know. So to apply the edge detection, we can apply the correct parameters. So this would be the data type for the output image of our gradient edge detection algorithm. The direction of the kernel, the size of the kernel, the scale, and no shifts, and specifying what happens at the border. Positional argument. So grad x. Now it's, if we now look at the output of grad x, top 5 pixels, and those are all 0. And then gray image. And the gradient in the y direction, which would be the 0, 1 direction. And they're all zeros. So what I want to do next is convert the scale it up to be between 0 and 255, because right now our response is not large enough. God, this is all dark. What image color thing is this? Ah, first that should be grad, not grad x. It's still all dog. That can't be right. All just zeros. $40 by $230, okay. Somewhere. Q and Q. Ah. I wanted to follow the exact Python code instead of using my own function, and then this is what happens. Okay, that's abstract x, abstract y. Okay, and here we add together the x and the y gradients after scaling them. And you can look at the scaling operations. We take anything from -50 and then scale it into the range by using the absolute value. So all the negatives are wrapped around. Because the Sobel edge detector, if it's from black to white, then it will be a very large positive response. If it's from white to black, it will be very large negative response. So that's why we would like to just map it to the absolute value. And here let's use a larger data type. So now we have the edges, the output of the Sobel edge detector. Actually, let me plot it in two and this will be Sobel Y, and maybe a little bit easier to see then. And here's the output of the Sobel edge detector and the Sobel Y. Oh, I didn't want to show those. I wanted to show the absgrad Y and the absgrad X. And here's our output. This one here, more response on horizontal edges, this one here more on vertical edges. The wings of the bird are sort of at a 45-degree angle, which means we get similar response in the X and the Y direction. Right? Here it tapers off a little bit. Now, if you look at that image, then you can see maybe already some of the problems, in particular here in the Sobel edge detection. On the width of the wing, there's actually 2 pixels on the edge rather than just a single pixel. If I zoom in there, then you can see that it's 2 pixels. Right? Also here at the side of the bird. So that's not what you usually want if you want to detect an edge, right? You just want a single pixel to indicate that there is a edge there. Also, of course, usually what happens in this kind of processing is that if you have a gradient response image, let's take that one here. And then you want to find edges, then whether something is an edge or not depends on the strength of the response. So let's pick a value here, and let's say we only want to highlight pixels that are above a certain threshold, right? So let's say I say everything above 128 is a edge pixel, then this is actually pretty easy to write in NumPy using Boolean arrays. Then I simply set it to 255. If it's greater than 128, and let me see if I can do that in one command. Let me see if that works, just out of interest. I have to convert it to a NumPy array. In that case, I just do it like that. So this will be our threshold image then. And you can see, actually that gives us a pretty good outline for the bird. Unfortunately, there's some spurious edges here on the wings, also in the forest, here. There's also some holes, right? Like this part here, and the beak is not identified exactly. So now I can change my threshold, of course. I could say, oh, I want I would like to fill these holes, then I can increase the threshold or decrease the threshold for what I accept as an edge pixel. But if I do that, then there's a good chance I also get some other noisy pixels. So let's say instead of going with 127, we go to with 100. Now you can see we get another couple of pixels here, but we also get more pixels in the background that we now accept as edge pixels. Also here in the wings we get some more edge pixels. And what location would that be? Let's say 142. Let's zoom in on one part of the edge image. We use zoom, so now what I want to show there would be, let's say 320 by 240, so that would be 100 to 140 and 150 to 190. Let's try that. One, two, one, 1, 2, 2. Did I not run this? Crash. Ah, Okay, now it worked. No idea why. So you can see when I zoom in on this area here, where we have the shoulder of the bird, then there's multiple pixels across here that are all classified as edge pixels. So so how would you overcome this problem? If you're looking for a maximum, right, we want to find a maximum in the image change, then we need to calculate the first derivative, but in order to test whether something is truly a minimum or a maximum or a saddle point, you also need to consider the second derivative. So using the second derivative, we end up with second order operators. And the most famous one of those is the Laplacian of Gaussian. So here we start with our original image. And the idea is to look for a zero crossing of the Laplacian, because the second derivative tells us if the function is sort of curving to the left or curving to the right. If that switches, then we actually would have an edge. And let me try this new drawing program. Say our image function here is an edge. And if I look at the algorithm, then just in one particular row, then let's say it goes like this. Here's our image function, the response for that image here. Now, the first derivative, if I look at that pixel there, then they may be like this, right? This may be 1 pixel. And the second pixel. And both of those have big changes, right? The first derivative would be very high for both of those pixels, so both of them would be recognized as edge pixels. If I look at the second derivative, however, then that will be the change in the change for the first derivative. So here, first derivative is 0, right? Then it starts increasing. and then up here it starts decreasing. So our second derivative here would be greater than 0. And here it would be less than 0. Now here and here, both of those the first derivative would be greater than some threshold t. Does it say copy to SVG here?
Yes.
Okay. And let's try. Yeah, that looks pretty nice. Cool. So instead of using the first derivative only, we can look for a crossing of the second derivative from greater than 0 to less than 0, and there's only going to be sort of one position at which this will happen, right, given an edge. And that's what the Laplacian operator, or in fact the Laplacian of Gaussian, and I'll get into why it's called that in a second. That's why that operator is based on. So if we're a continuous function, then we could look for the exact point where the second derivative is 0, but of course that's unlikely that this will happen just exactly on a pixel boundary. So that's why we only check one part where the second derivative is positive, and then another pixel where the second derivative is negative. If we assume that the function is continuous, then the point where it switches has to be somewhere between those two pixels. But it wouldn't be at pixel 412 or 413. The exact point may be pixel 412.21 or something like that. So this is what we can implement. Here's our image. So now how do we estimate the second order derivative? If I look at a 5 by 5 area as a convolution mask, right, then the center pixel is here, P00, and then I have other pixels here, P minus 1, P minus 2, 0, minus 1, 0, 0, 1, 0, 2, 0, 2, 0, not 2 minus 0. And here I would have P minus 2 minus 2, P minus 1 minus 2, 0 minus 2, 1 minus 2, 2 minus 2, minus 2 minus 1. So this is just a 5 by 5 convolution mask. So the question is, if this is what I call the pixels, then how do I calculate the second derivative? Now calculating the first one, we said that's pretty clear. In the simplest case, it would be the difference between P10 and P minus 10, my right neighbor and my left neighbor, in the x direction. xy would be P01 minus P0 minus 1. Divided by 2 then. Which corresponds to the Sobel edge detection approach, right? That's exactly what we're calculating there. So how about the second derivative? The second derivative, what I want to find out is the change in the first derivative. So how can I calculate that? Well, the first derivative of this pixel. How do I calculate the first derivative of this pixel in the x direction? The same way that we can do it for this pixel. So it would be this neighbor minus this neighbor. Right? And that would give me an estimate of the first derivative for this pixel. This neighbor minus this neighbor would give me an estimate of the first derivative for that pixel. The second derivative would be the difference then that I calculate for the first derivative of this and the first derivative of that pixel. So we calculate the first derivative in x in the positive direction, P10 minus P00, and in the left direction, P00 minus P1, 0. Now I need to look at the difference between those two. So I get P10 minus P00 minus P00 minus P minus 10. So that ends up with this equation. Now I can apply the same idea for the vertical, and in that case I end up with this convolution mask, which allows me to calculate the second order, the second derivative response of the image. So here we can implement that. So we have an original image converted to color. Converted to grayscale, not converted to color. And what I wanted to do was here it is. Here's another code again to show a Sobel X and Y direction. But this time it's scaled to be 128, so show positive and negative. So this is not using the absolute scaling yet. And now I can calculate the Laplacian operator on the region of interest, which would be, here I calculate the Laplacian as well. So you can see these are actually just 1 pixel boundaries here. Also in compared to the Sobel. And then I can zoom in and show the output of the Laplacian operator. So here we only have a single pixel then, as opposed to here multiple pixels. So in that scenario, the Laplacian operator actually works a lot better if we scale it and use the absolute, then it will be a very nice thin line that separates out the bird for this whole area here. So things look very good for the Laplacian operator. It seems to be doing a better job on our bird image than the Sobel-based approaches. And since I can represent it as a 3x3 convolution mask, computationally it's not any more expensive. One thing that we do lose by using this approach is that I don't get any gradient information. All I get is that there is an edge pixel but it's not directed anymore. I can't tell if it's a vertical edge or a horizontal edge. So in a sense, that is an advantage often, right? If you only care whether it's an edge pixel or not, you don't care about the gradient direction, then of course if you get both in one sweep, it's twice as fast as the Sobel edge detection algorithm, because I only need to run it one time. But now let's have a look at the same image, except I add a little bit of noise to it. So here I have my original grayscale image, but then I add a pixel noise of maximum 3. No, not a uniform noise. It's a Gaussian noise with mean 0 and standard deviation 5. So now we can look at that image. So here's our original image, here's our image distorted by noise. And you can see that it's actually quite a bit of noise, right? You can see the random pattern in the image now here. So what do you think will happen to our Laplacian operator now? We can zoom in, first of all. And you can see the noise pattern in the image here. Now we can calculate the response of the Laplacian operator and the Sobel operators in the x and y direction. I can change it to 3 again here. And then I threshold the images. And then we can have a look at the response of the Laplacian operator. And if you can believe it, for the Laplacian operator, adding the noise is brutal, right? The bird basically disappears now. Everything becomes an edge pixel or not an edge pixel. If you know where the bird is, you can sort of see the outline. But other than that, it's a complete mess. And if you think about it, that makes sense, right? Because if we look at this picture here, we define an edge now by the second derivative switching over from being greater than 0 to less than 0. So that means that the height of this edge here doesn't really matter. If this is from 0 to 255, the second derivative is going to switch from being positive to negative, right? Because it's going to go up to the next pixel. So in this case, it's clearly an edge because it's sort of the maximum difference. So if you cannot detect an edge from 0 to 255, then you won't detect anything as an edge. Then nothing is an edge. For the zero crossing operator, Laplacian operator, however, if it is flat and there's one pixel that is one above, then that is also going to change the second derivative, right? Because it doesn't matter how high this peak here is, the fact is the function is going to go up and then it's going to level off. So if this is only one pixel, then that's enough for an edge if we look at the second derivative. So if we have noise and then we add a pixel or we subtract a pixel, we're going to introduce thousands of edges into our image, which is what happened here. There are edges everywhere now, right here. So how can we solve that particular problem? And by the way, the same thing would be true for any other kind of algorithm that you can think of that uses the second derivative. Right? And yes, it's easy to see that the Laplacian operator is very sensitive to noise. So what we need to do, otherwise the Laplacian operator works really well, it's just very sensitive to noise. So what we need to do is get rid of the noise in a sense, right? So how can we get rid of the noise? Well, one way to do that, and a very common way, is to use blurring, right? To blur the image. And one of the most common ways of blurring an image is to use a Gaussian blur and apply that to the image. So we can have different kernel sizes, look at a region of interest, and then apply the Gaussian kernel to it. Then I can calculate the Laplacian, threshold it, and generate the output images for Sobel and the Laplacian operator. I forgot to mention, of course, here's the Sobel edge detection. Sobel edge detection is much less affected by the noise. Right? For Sobel, if there's some noise in the image, it's not a huge problem. So here's our output of the Laplacian, and now we have the Laplacian operator with a Gaussian blur applied first. And now you can see this is a lot more reasonable again. Now you can make out the shape of the bird. So that's why the operator for edge detection is usually called the Laplacian of Gaussian, the LOG operator, because without the Gaussian, you usually cannot apply it. You need to reduce, you need to blur the image first in order to avoid getting too many spurious edges, too many ghost edges. Now, with our blurring, we also got rid of some of the pixels that are part of the outline, right? Like now we have a lot of holes here after I blur it. But single nice shape other than that. And but so which one is better? Well, like most areas of computer vision, robot vision, artificial intelligence in general, machine learning in particular, it depends very much what your application is. And in fact, without a particular application in mind, it doesn't really make sense to talk about the performance or the quality of an edge detection algorithm. Now, Sobel and other first order operators have the advantage that they're fairly robust to noise. Have a disadvantage that you often get multiple pixels per edge. The other advantage that the Sobel and other edge detection algorithms have that are first order operators is that they also provide you more easily with a complete outline. The Laplacian second order operators have the advantage that they only give you single pixel edges usually. And so they have a nice thin outlines. But their disadvantage is that they're very sensitive to noise So we usually must apply a Gaussian blur first. And they often have holes in the outline. Like if you look here, there's pixels missing. So in a sense, the two algorithms have opposite strengths and weaknesses. Now this can be actually generalized and is true for any kind of classification algorithm. So when we talk later on about object detection or face recognition, and even any kind of machine learning algorithm where you classify objects into positive and negative or small, medium, large, or whether this is a dog or a cat or an elephant, any kind of algorithm like that, they usually have two error classes. One are false positive, and the other one are false negatives. Now in practical applications, in most applications, the penalty that you have to pay if you make an error, they're not symmetric. So usually one kind of error is worse than another kind of error. So false positive means that you detect an edge pixel even though there is none, right? And a false negative would be that you do not detect an edge pixel even though there is one. So here in this case, Laplacian, these would be a lot of false negatives, the holes here. In the Sobel edge detection, the multiple pixels here would be false positives, examples of false positive errors. Now, depending on what your application is, the penalty is not symmetric, so you cannot simply just subtract it. Then that's then where the choice of algorithm becomes crucially important, because if you have an algorithm that is more likely to produce false positives, then you better have an application where false positives are not a big problem. If they are a big problem, you want to pick an algorithm or a setting. Sometimes you can also tune your algorithm to generate more false positives or false negatives. You want to tune your algorithm in such a way that the less severe errors occur more often than the more severe errors. So let's think about some applications in edge detection. Let's say I have a machine vision system to detect errors in a painting job for an airplane, for example. Right? Or I'm building a ship, and it's a huge ship, and I have a little robot that goes by, and I need to check if the rivet holes are all correct at the correct location or not. If in that application, most likely to have extra pixels that detect edges is going to be problematic. Whereas holes, pixels that are missing because you want to fit a circle on top of it or a straight line on top of it, as long as you have enough of the true edge pixels, that will still be good enough. So even if you have a hole in your outline, it wouldn't be a big problem for such a system, assuming that you sort of fit circles to rivet holes in order to make sure that the size of the holes are correct. Other than that, if you run a conveyor belt, system to detect bad potato chips on an assembly line. We actually had a problem like that in New Zealand where the company was producing potato chips and they were running down on this conveyor belt, and they wanted to make sure that the potato chip is not too wet, because if the potato chip is wet and you put it in the bag, then it's going to mold and it's going to destroy the whole bag, and it's very disgusting smell when you open it. So if a customer bought a bag where they had put in a moist potato chip, then not only would it ruin that bag, but the customer would never want to buy that particular brand ever again. So in that case, if you detect a whole bunch of spurious potato chips, let's say, but the probability that a potato chip was bad was actually pretty low because they had their processes under pretty good control. So if you have a system that generates lots of spurious potato chips, then they weren't really moist, and you detected that with the edges on the infrared image. If the edges were too strong, we were looking for edge pixels, then it would stop the assembly line. They would need to check the chip out, and then that would cause a huge delay. Right? Then false positives were a big problem. Something like that. So here false positive on the edge pixels, but more importantly, so here So their false negatives weren't a big problem. So false positives were a bigger problem. So that means if you find random holes, right, that would be a bigger problem. And here, actually, the false negatives were a bigger problem. Because if you say it's not moist, but you put it in the bag, then the customer would never want to buy it. And this kind of trade-off, it's very important to realize that in lots of different applications of machine learning AI. It's very important to understand the importance of the different types of errors. And also what's important is the prior, this applies to lots of other domains. Also, if you have skewed priors, so if you have many positive examples but very few negative examples, then the whole thing becomes even more difficult. So that would be, in an example would be if you're trying to implement a system that detects if somebody is carrying a gun onto an airplane, right? So you want to look at the image on the X-ray machine, but instead of having a human do it, you want the computer to be able to do that and to detect guns being carried on an airplane. Then of course the false negatives are a huge problem, right? Because if you say that this person doesn't have a gun and he goes through and then attacks a terror attack, that would be possibly thousands of people died because your system didn't work properly. So in that case, you would have to go with more false positives. So you will pull out people that don't actually have guns. Most likely, you will have to tune your system in such a way that you will stop people that don't have guns and search their bags, especially, for example, or interrogate them or something. The whole thing is made more difficult because every day millions of normal people, non-terrorists, travel, but every year, luckily, there's only a couple, one or two terrorists per year, terror attacks, hopefully, right? So the chances are skewed very much against being able to detect a gun from the beginning. So in other words, if you just say no gun all the time, then you're probably 99.9% correct. But you cannot allow the 0.001% error that you still have in your system. The whole point of the screening is to absolutely make sure that there never is a gun on an airplane. Let me just take a short break. I need to go to the washroom. So think about how you would try and solve this problem for things like checking bags for people getting onto an airplane. Okay, so we're back. Attack. So these vastly different priors will cause a problem, because even if I just say always no gun, then I'll be 99.99% accurate. However, in this particular application, that wouldn't be good enough. Of course, the other extreme would be, you may decide that you want to say search everybody's bags. And it will cost a lot of time and money. So finding the right balance, finding the right tuning for your parameters is actually very, very difficult in those kind of scenarios. And just like lots of other applications of AI, machine learning, intelligent robotics, there's no one best algorithm or one best answer. You have to very much understand your domain, understand the trade-offs between your errors, and then come with a system that balances the penalties, the priors, and the accuracy of your system into a working, manageable application for the real world. So let's run this. But I like this Excali draw. This makes very nice drafts. I'm going to change my drafts over to this. The hand-drawn one. Okay, so later on you'll be able to click on here and get the PowerPoint image slide representation of this. What is this now? Okay, this is a collab link now. Very weird. Yep. Say again, what? The latest row. Yeah, I haven't written it yet. Yeah. Just give me a second. So let's take the picture of the bird. And resize it. So that one. Actually, one thing that I forgot to mention is here, for the Laplacian operator, if I only look in vertical and horizontal direction, I would end up with this, right? 111 minus 4. But I can also extend it and the one we usually use we can also extend it for diagonal edges. Right? So not just above, below, left and right, but also top left, top right, bottom left, bottom right. In which case our operator would look like this. Right? Doing the same reasoning, I would end up with operator in all directions. That's just an extension of this to also include the diagonals. Then you end up with this operator. So let me just run that. And here, the canny edge detector. Is a popular general purpose edge detector. Most people, if they just want to detect some edges, they don't really care about the trade-offs or the advantages of first order, second order systems. They will use the canny edge detector because it gives good results in a large range of different applications. It is based on, it's an extension of the Sobel operators. So it runs Sobel Edge, Sobel X and Sobel Y first. But then it has a couple of extensions in order to make it more, make it a better edge detector, or to reduce some of the problems with Sobel operators. In particular, first thing, it uses a hysteresis function. So what does that mean? This is actually an important concept to learn from control systems engineering. There's many applications of using robotics where hysteresis functions turn out to be extremely important. One example would be let's say you want to develop a robot that follows since we were talking about an airport, that follows you through the airport. Like an automated, autonomous baggage cart, right? Then you want it to follow closely. So that nobody can cut in front of you, otherwise the robot, the carrier, is going to be confused about who to follow. right? So you want to follow at a reasonable distance. So you don't want to be too far away, but you also don't want to be too close, because otherwise you keep bumping into the person. So let's say you want 1 meter distance. Then how do you write the Python code to do that? How would you implement that? Hmm? Yeah, use some sort of sensor. So you have ultrasound, let's say, or LiDAR, right? And then you would write most likely you would write something like this: if distance to person fits. Okay, let's go with greater than 1 meter, then what? Then move forward. Right? Maybe not speed up, but move forward. Otherwise, if the distance to the person is less than 1 meter, then what? There's no then in Python. Sorry. Move backward. Okay? So lots of people will implement it this way. And then what will happen? Well, what will happen is a very nice dance, because if I walk and the robot follows me, right? Then everything is usually good, right? Because I keep moving, the robot will follow me. Then I stand still. Now the robot is at... Yeah. Because the only time it will not move now is if it's exactly at 1.0000 meters. So it'll be 101 meters, so it's going to go forward. And say, oh, now it's 98 centimeters, so now I go backward. So now it's 1.05. Okay, then I go forward. Oh, now it's 95. Oh, then I go backward. Now it's 98. Okay, then I go backward. Now it's 103. So now I go forward again. So the robot is constantly going to move, which is also not very nice for the people, right? Because they're standing still. They expect the robot to stand still. Even if the person is not nervous, it's a huge waste of energy. You're constantly moving the motors even though there's no point. So what you need in order to solve that is a hysteresis function. And by hysteresis, that's just a fancy name for dead zone. So what do we mean by dead zone? In the control, Okay, maybe let's make it look like this. That still has the same problem. So the problem is the robot will oscillate between two behaviors, moving forward, moving backward. Because chances that it'll be at exactly 1 meter are extremely slim. Right? So with the hysteresis function, if last command is, you would implement something like this. If distance less than 0.95 meters, then definitely move, if distance greater than 1.05 meters, then definitely move forward. Else, if the distance is less than 0.95, meters, then definitely move backward. Where this would be called the high value, and here we sort of have a low value. So now our dead zone is defined by the values that are between high and low. So in this case, what do we want? No, not necessarily, because if I stop there, then I may miss the person when they walk away. In that case, what I want to avoid is oscillation. So I want to avoid the system moving forward into the zone and then backwards out again, right? If the person is further away, I want to be able to go forward, that's okay. And going backward is also okay. I just don't want to switch the behavior. So it would be if previous command is equal to and now I want to check if I'm greater than 1 meter or not. So if distance is less than 1 meter and previous command is equal to distance is less than 1 meter, so I want to move away, and the previous command is move backward. then I want to move backward. Else, if the distance is greater than 1 meter and the previous command is move forward, then that's also okay. Then I move forward. And else we stop. Oh, and then I can update previous command. Like this here. So this will be a hysteresis function. The canny edge detector uses that with low and high, except for detecting an edge pixel. So if the Sobel output is greater than high, then definitely edge, right? If it's actually, I'm not quite sure what let's see. I just want to check if it checks the gradient direction. I know canny edge detection uses the gradient direction, but when it merges the edges, does it use So it's like that. So if the Sobel response of a pixel is greater than the high threshold, then it's definitely an edge. If it's less than the low threshold, then it's definitely not an edge. If a pixel is in between low and high, and one of the neighbors is an edge, then that pixel is also an edge. And if it's not, then it's a non-edge. Okay, so within that range between low to high, we're not allowed to change our mind about something being an edge pixel or not an edge pixel. Then the Kenny edge detector does another couple of things. One of the things that we noticed for first order operators was that we often get very thick lines, multiple pixels to represent an edge. So to avoid that problem, the Kenny edge detector uses local non-maxima suppression, which means that if we have a direction for the gradient and we follow that direction, and then we check the Sobel response, and only the pixel that has the maximum response within that neighborhood will be classified as an edge. So we suppress neighbors that have non-maxima Sobel response. To avoid multiple edge pixels for an edge. Which is a common problem for first order operators. And that is done in the direction of the gradient, in the direction of the edge. So this is sort of an extended algorithm. You have to do several passes over the edge pixels. You cannot implement it using a simple convolution mask. The first steps, of course, Sobel X, Sobel Y, are using the convolution. But you have two passes of convolution, then you need to check for the hysteresis function and the non-maxima suppression. But it runs fast enough, so you don't need to be concerned about the runtime of that algorithm. So let's just implement it quickly, or you can implement it as your homework. Let me just okay, good.